Good morning everyone. Today we will discuss about the kinetic theory of gases. The kinetic theory of gases is a basis for all the gases. And in the case of gases generally, we will discuss about the thermodynamic parameters. What are the thermodynamic parameters? Pressure, volume, temperature. So these are called generally macroscopic parameters. And a bigger size, we can measure them like that in terms of the pressure and all. But actually you go inside, the deeper into the part of the topic, why this pressure is coming, why this temperature is coming. So these points are discussed under the kinetic theory of gases. They want to derive a simplified formula in a macroscopic manner in terms of the pressure to make the calculations of every individual particles. So you know how difficult to manage with every individual particles. Therefore, they generalize the equations by making some assumptions. Whatever they are doing is valid under these particular assumptions. So then only it leads to the general equations like PV is equal to nRT. Otherwise van der Waals equations will come. P plus A by V square into V minus B is equal to nRT. That is called van der Waals equation. Van der Waals equation is valid for the real gases. Real gases you are talking means there is no assumption required. Really the conditions will consider. But in these cases, to make the calculations simple, so they make some assumptions. Basing on these assumptions, they derived the equations. So that is the reason why kinetic theory of gases, while studying, we have to remember on what assumptions they derived this particular lesson. So this you understand, topic is going to be very simple. Now we look at what assumptions they made. All the gases are made up of molecules moving randomly in all the directions. You know the Brownian motion. Generally every gas molecules move randomly, this side and that side and that side, like that. They're going to move randomly in all the directions. That happens in every time, every moment because of any temperature existing. So they move randomly in all the directions. The size of the molecules is much smaller than the average separation between the molecules. So molecular size is very small, and this is like distance between the molecules is going to be little larger. So what actually this means? When you are talking about the collisions and the length of the room, distance between the molecules and all, if the size of the molecules are very bigger, so you have to calculate the center of mass of the molecule to that center of mass of the molecule. So they don't calculate like this. Calculating like this is very difficult, no? So that is the reason why they are assuming that sizes of the molecules are point sizes. They don't have any significant size. Generally, to achieve this condition, what they can do is, if the density, for example, they are doing experiment, in the less amount of gas is there is a low pressure is existing. Low pressure is existing means naturally density will be very less. So one molecule is going and hitting that wall. In the meantime, they collide with the molecules also. So this probability is going to be the less. So that is the reason ideal gas equations are valid at the low pressures. Next, the molecule exert no force on each other or on the walls except during collisions. So when the collision is taking place, in between one is not exerting any pressure on that. Why and how? Whenever it is colliding with the other, it gives a momentum of mv, bounces back with a momentum of mv if the collision is perfectly elastic collision. At that time only, pressure difference, momentum difference is nothing but rate of change of momentum if you calculate it for 1 second. The rate of change of momentum gives force. That force per unit area gives pressure. Like that they are calculating the pressure. If the intermolecular attractions are there, they also can exert some pressure, no? But they are not considering those pressures. That is the reason why molecules at distance are going to be very large. Molecular attractions they are not going to be centralized. So that is the reason why molecular interactions will exist up to certain distance. Beyond that, they won't exist. That is the reason pressure because of the intermolecular attractions is simply neglected if the distance between them is very large. Where they are considering the pressure, only they are colliding with the walls. So for that reason, they made this assumption. All the collisions are perfectly elastic Also, the time spent during the collision is negligibly small. All the collisions are perfectly elastic. And actually here the calculations are little interesting. For example, here is one substance, here is one molecule. So one more molecule came. This molecule is coming and hitting this one. If the two molecules are exactly equal, between two identical balls undergo elastic collisions, they exchange their velocity, this during collision. This is coming and hitting. This comes to rest and this will move. Okay, this is at rest. This is coming and this is hitting with this one. So this is coming here. So in this case, one can calculate in such a way, actually it is here coming and hitting this one, this is coming to rest, this is continuing. One more molecule came and that molecule is in the path of this is hitting this one, this is coming here. Here the time spent is very, very small. You can calculate in such a way, now the molecule is straight away traveled from here to here, right? So that they are taking. Actually, single molecule is unable to reach that up to the wall. It is a very difficult phenomena. One is coming and hitting, that is moving, that is hitting another. Finally, one is reaching the wall. Okay, the velocity with which it is coming and hitting, that is giving the velocity to this. This is giving the velocity to this. Finally, the molecule which is hitting the wall is having the velocity of the first molecule. So therefore, we can simply say that, so that molecule is hitting the wall. Calculations will be very simple. So for that reason, what they are saying, time spent is very, very small. For example, it is coming slowly, hitting, so these two are spending some time here and then going means you can't take that molecule traveled there because time lag should be counted. So that is the reason why, to make that assumption, to make the calculations simple, time spent during the collision is negligibly small. Therefore, this molecule is straight away reaching the other. Like that you can take instead of entertaining many collisions for simplicity. Next, the molecules obey Newton's laws of motion. Newton's laws of motion means simply a body continues to be a state of rest or of uniform motion unless it is compelled by an external force. Rate of change of momentum is equal to force. By using these calculations only, we are going to calculate the equations in case of kinetic theory of gases. And one more important assumption they made is, when a gas is left sufficient time, it comes to steady state. In the same room, one end is at higher temperature, another end is at lower temperature. So then what would happen if you provide some time, heat travels from a body of higher temperature to a body of lower temperature until they gain the same temperature. Next, you provide sufficient time, what happens is, the wall is also maintained the same temperature of the gas. If not, what would happen? If the gas molecule and hit this, because if the temperature of the wall is high, this molecule's shape is going to out. When molecule shape is out, so some deformation is taking place. Deformation is taking place, definitely there would be some loss of energy. So if there is a loss of energy, it is not perfectly elastic collision. So that assumption is going to fail. That is the reason why you provide sufficient time, then temperature of all the gas molecules would be same. Temperature of the wall is going to be the temperature of the gas molecules. So then perfectly elastic collision condition is going to be satisfied. And one more thing is, at any given instant of time, the distribution of the gas molecules, the velocity of the gas molecules is not going to a function of space and time. So that is the meaning of this expression. The density distribution of molecules with different velocities are independent of position, direction and time. So what is the meaning of this? So one molecule is maybe going in a direction, that hits other molecule. Anyway, the number of molecules in a particular direction is not going to change, even though some other molecules are coming and hitting this one. For example, one gas molecule is moving with a velocity Vx in this direction. In the same time, there is a velocity, gas molecules which are in this direction is also going to be Vx, but we are calling with the name of Vy. And a number here, number z-axis, all are going to be the same. Vx, Vy, Vz are same. number of molecules moving along x direction, number of moving along minus x direction is also same. Means across this cross section, 4 molecules are going in this way, 4 molecules are going in this direction. So net is going to be how much? 0. So that is across any cross section, number of gas molecules moving from left to right, number of gas molecules moving from right to left are going to be same. That is the reason why distribution is also not changing. So these are the very great assumption which is simplified the complications existing during the collisions in case of the gases. So under these assumptions, equations which were made are called with the name of ideal gas equations. Pressure, volume and temperature are going to be established by using these relations. By taking those relations, later gases and other topics are going to be thermodynamic parameters, everything were established. Now we will continue the topic by deriving the pressure of an ideal gas. Actually, we may feel that what is, just simply we can remember the formula. But in writing the formula, where we'll get confused is, sometimes the calculations work for molecules. Sometimes they give the molecular weight. Sometimes they give the mass. So molecule mass is small m, molecular weight is capital M, mass of the gas is m. Now, which m you are using in this case? So that is to be recognized first of all. So that's why I'll try to give I try to establish a relation between them by using a derivation. Look at this. This is the room. All the gas molecules are coming and hitting the wall along the x direction. Remember, in the same time, y direction collisions are there. In the same direction, z direction collisions are there. X, y, z direction, everything is there. I am calculating only for x axis. Same thing I replicate along y axis and z axis also. So here I am using the force definition. Force is equal to rate of change of momentum. So it is hitting with mv, bouncing back with mv. So what is the change in momentum? This is plus mv, that is minus mv, change is 2 mv. Rate of change in momentum is equal to force. This is the first statement I am taking. Next, what is the time interval you have to consider? Remember, if this is the wall, if it is going, molecule from this end went on and hit it, again it may went on and then coming back and hitting this. That is called a second collision. At the point hitting, again hitting at the same point is nothing but the time interval between 2 successive collisions, not from only here to here. So that is the reason why going is L, coming back is L, along x direction, time is equal to displacement by velocity. Therefore, 2 mvx by t, t is equal to 2L by vx. So 2 cancel, this is becoming mvx square by L. This is the force. This is depending on x direction, m, L. M is the mass of the gas molecule. Small m is the mass of gas molecule. Velocity along x direction. But the same particle may not be moving horizontal. Now this gas molecule may be moving in this direction. It has the 3 components of velocity Vx, Vy and Vz. Now we calculated only along x direction. Now all the 3 together will give you velocity of the gas molecule. So now we use the statement, the density and distribution of the molecules with different velocities are independent of position. Now Vx, Vy and Vz all are equal because the distribution is not changing. So first one molecule, Vx square, Vy square, Vz square, same. For all the molecules we are considering, sigma Vx square is equal to sum of all the 3 by 3. Sum of all the 3 by 3, because all are same. You add these 3 divided by 3, you can get the same value. For example, 5, 5, 5 like this, 5 plus 5 plus 5 by 3, you can get the same 5 only. But we are expressing in term by taking consideration of all the directions. So that is why sigma Vx square, sigma Vy square plus sigma Vz square. So is equal to sigma of Vx square plus Vy square plus Vz square by 3 is taken as Vx square. And this is by taking the information from all the directions. By 3 we are taking, it is nothing but one direction. Now, we are using this equation in this part, sigma into Vx square. Why sigma we are taking? This is a pressure created by 1. Sigma is giving average pressure, average force created. This is a force in a direction. This is going to be average force because of all the directions. So, therefore, this is m by L, 1/3 sigma V square. Now, V is the velocity of the particle. V is the velocity of the particle. Earlier, Vx is the velocity of the particle along x direction. Vy, velocity of the particle along y direction. Now, you look at this. Now, in this expression, I am multiplying with n, dividing with n. This n is what? It is not Avogadro number. This is total number of molecules existing are n divided by n. Therefore, n into m is nothing but the mass of the gas. N molecules are there. Each molecule has a mass of m. Pressure is equal to force by area. This is force by area. Area, here I am writing A into L. N into m is mass of gas, is called mass of gas. Mass of gas which is given to us. Mass by volume is equal to what? Mass by volume is density, 1/3. So, this is V1 square plus V2 square plus V3 square etc. divided by n, RMS velocity. What is the meaning of RMS velocity? RMS velocity. First you take the squares, V1 square, V2 square plus V3 square. Sum of all the squares by number, which is nothing but mean. You take square root. So, this is called with the name of RMS velocity. Square it, mean it and root it. So, VRMS square means V1 square plus V2 square, V3 square by n. So, therefore, this is nothing but V1 square, V2 square is sigma V square by n is equal to VRMS square. So, that is the reason why in the place of this we are writing VRMS square. Therefore, pressure is equal to 1/3 P into VRMS square. This is macroscopic formula, big formula. And now onwards, they give the data as the pressure is given, what is the RMS velocity? Pressure is given, what is RMS velocity? Then you have to use the formula. So, like that we can establish some more relations for this RMS velocity. This is the basic way of generating the pressure equation. One more point I want to introduce. I am multiplying with volume. P into V. P into V is 1/3 rho V RMS square. Rho into V. What is rho? Density of the gas. V is what? Volume of the gas. Rho into V is what? Mass of the gas. Okay. PV is equal to 1/3 m V RMS square. PV is equal to 1/3 m into V RMS square. Here m is what? M is mass of gas. Mass of gas. It is not the molecular weight. This is the mass of the gas. Here in the place of PV, you can write nRT, right? In the place of PV, you can write nRT. So, like that also, you can calculate the VRMS square. This formula will establish a bit later again. So, this is one basic formula. This is another basic formula. So, you have to remember these formulas. How the link has been generated also, you try to remember. Next, I am doing one thing. I am multiplying with 2, dividing with 2. Then what happened? 1/2, 2/3. Half mv square. M is the mass of the gas. Half mv square is what? Kinetic energy of the gas. So, kinetic energy of the gas is given by 2/3 K. K is kinetic energy. PV is equal to 2/3 K. PV is equal to nRT. nRT is equal to 2/3 K. So, therefore, temperature, kinetic energy relation is that one. In the place of that, you can write nRT. So, temperature is alone responsible for the kinetic energy. If the temperature is given, you can estimate the kinetic energy. So, that is the reason why PV is equal to nRT equation. PV is the representative of pressure potential energy. nRT is the representative of kinetic energy, like mgh is equal to half mv square in the mechanics part. So, okay, one more, you observe this. K is equal to how much? 3/2 PV. So, kinetic energy of a gas molecule is given by, kinetic energy of a gas is given by 3/2 into PV. In the place of PV, we can write nRT. In the place of PV, we can write nRT. Okay. Next. K is equal to, kinetic energy is 3/2 nRT. This is the kinetic energy of the gas. Now, this I will try to modify. Kinetic energy per 1 mole is how much? This is for how many moles? N moles. So this is for N moles. Kinetic energy per 1 mole is how much? 3 into 1 by 2 into RT. So this is actually later develops into, what is that? Develops into energy stored, principle of equipartition of energy. For each degree of freedom, 1 mole of a gas contains this much of energy. Contains this much of energy. We used how many variables? Vx, Vy and Vz. All the 3 are linear motion or rotatory motion. All 3 are linear motion. How many degrees of freedom? 3 degrees of freedom. Vx, Vy, Vz. 3 degrees of freedom. 3 degrees of freedom means it is which gas? Monoatomic gas. Monoatomic gas move liberally. There is no fixations for that. So that is the reason why it doesn't have any rotatory energy. It doesn't have any oscillatory energy. It has only linear energy. 3 forms. 3 into 1 by 2 RT. 3 into 1 by 2 RT. 1 by 2 RT. Energy stored for each degrees of freedom. For 3 degrees of freedom means how much? 3 by 2 RT. 3 by 2 RT is energy per 1 mole of a gas. Once again. 1 R is equal to, capital R is equal to, this is N is Avogadro number, K is the Boltzmann's constant. K is Boltzmann's constant. What is the definition of Boltzmann's constant? Gas constant for 1 molecule. Therefore, in the place of R, I will write Nk. That N I am sending here, 3 into 1 by 2 kT. What is 1 by 2 kT? This is energy stored per 1 degree of freedom in case of a gas molecule. This derivation comes later. All these steps we will repeat again. 3 degrees of freedom, 3 into 1 by 2 kT. 1 by 2 kT is kinetic energy per degree of freedom in case of gas molecule. 1 by 2 RT is energy per each degrees of freedom in case of 1 mole, and kinetic energy is equal to 3 by 2 PV for a given gas. 3 by 2 nRT for a given gas, because N moles we multiplied. Basing on the earlier discussions, I want to consolidate what formula existing in this to solve the problems on kinetic theory of gases. First, we derived a result. So these results you try to keep in mind. P is equal to 1/3 rho V RMS square. So VRMS formula is how much? Root of 3P by rho. Rho is the density of the gas and P is the pressure. You should have to write that one in SI units. Means 1 atmosphere is equal to 10 to the power of 5 pascals. So here you can get one type of problem. Next, I am multiplying PV is equal to nRT. PV, volume is equal to mass of the gas by density, and also mass by molecular weight into RT. So P by rho is how much? RT by M. Therefore VRMS is equal to square root of 3 RT by M. VRMS is equal to how much? Root of 3 RT by M. They give the two different gases at temperatures, different temperatures T1 and T2. VRMS values are given by. So T1 by T2 by M2 by M1. So from this discussion, V1 by V2 is equal to root of T1 by T2 into M2 by M1. So this means at a given temperature, velocity is inversely proportional to its molecular weight. Velocity is inversely proportional to molecular weight. Means oxygen and hydrogen. These two gases were there, which has more velocity. Velocity is inversely proportional to molecular weight. So molecular weight is more for oxygen. That is the reason why velocity of the gas molecule will be less in that particular case. To solve such a type of problems, this formula is useful. Next, RMS values of a given mass of the gas. Some mass is given, find out RMS velocity in that cases. PV is equal to 1/3 rho V into VRMS square. This is for V is volume, just multiplied with E on both sides. PV is equal to 1/3 mass into VRMS square. So VRMS is equal to square root of 3 PV by mass of the gas. 3 PV by mass of the gas, this is. Okay. Next, kinetic energy of a given gas. PV is equal to here 2 by 3 This is actually 1 by 3 mass into Vrms square. I multiplied with 2 and divided with 2. Half into mass of the gas into Vrms square. So 2 by 3 into kinetic energy of the gas, given mass of the gas. So now the gas is given, the pressure of the gas is given, volume of the gas is given. Find out its kinetic energy. For that question, the formula is K is equal to 3 PV by 2 or 3 by 2 nRT. 3 by 2 PV is equal to nRT. So kinetic energy basing on temperature 3 by 2 nRT. So which kinetic energy here? Kinetic energy is translatory kinetic energy. Remember, translatory kinetic energy is decided by the temperature. So temperature is because of translatory kinetic energy of the molecules. Fine. So kinetic energy of 1 mole of a gas is equal to how much? Kinetic energy per 1 mole is equal to 3 by 2 RT. Next. Kinetic energy of 1 molecule of a gas is how much? Kinetic energy per molecule is 3 by 2 kT, where K is called Boltzmann constant. Boltzmann constant K is given by K is equal to R by Avogadro number. 8.314 by Avogadro number is 6.023 into 10 to the power of 23. So therefore, here R by N, 8.314 by 6. 6 is roughly 1.38 into 10 to the power of minus 23. So this is the Boltzmann's constant. Okay, Boltzmann constant definition comes here. So kinetic energy per 1 mole, kinetic energy per 1 molecule are differing. Next, what is the principle of equipartition of energy? Principle of equipartition of energy means kinetic energy will be distributed equally among all the degrees of freedom. How many degrees of freedom will be available? So monoatomic gas 3 degrees of freedom is available. So this is nothing but along x-axis Vx, Vy, Vz. And in this diatomic gases, in this Vx, Vy, Vz, Ix and Iy. Ix and Iy are moment of inertia along x-axis and y-axis. Moment of inertia along z-axis will be 0. So 3 plus 2, 5 will come. So this is about the diatomic gas. Polyatomic gas changes from situation to situation. In this 6 degrees of freedom will come. Next, from this how to estimate gamma? Gamma is equal to 1 plus 2 by F. Degrees of freedom is given 1 plus 2 by F. Take F plus 2 by F. So this is F, degrees of freedom 3. 3 plus 2, how much? 5. 5 by 3. 5 plus 2, 7 by 5. 6 plus 2, 8 by 6. In this way we can estimate the gamma. Gamma value is given, we can estimate degrees of freedom. Here is the source for the problems. Next, relation between absolute scale of temperature and kinetic energy. So this is a one relation which is established. PV is equal to 1/3 m into Vrms square. That formula already derived. Pressure, same equation at a triple point of water we are calculating. Same equation is valid. Velocity Vrms at triple point. Pressure is also at triple point. P triple point into V is 1/3 m mass of the gas into Vrms at triple point. Now you divide one with other. P by P triple point is equal to V square by V triple point square. I am keeping this equation. We know pressure is directly proportional to the temperature. P by P triple point is equal to temperature by temperature of the triple point. Triple point of water is 273.16 Kelvin. So therefore, T by 273, this is T by 273, P by, here earlier what relation we got? So this is given by V square by Vt triple point square. So therefore, T is equal to 273.16 by triple point velocity Vrms into Vrms square. So temperature is directly proportional to square of Rms velocity is the result we are getting. So Vrms at triple point is a constant for a given gas. Vrms value at triple point is constant. So that is the reason why this is taken as a constant. So this is next. The absolute temperature of a sample of proportional to the translatory kinetic energy of these molecules. So this is the meaning of that. Absolute temperature of a sample is proportional to translatory kinetic energy. Translatory kinetic energy. Why? Kinetic energy is given by half mv square. It is proportional to square of the RMS value means it is proportional to kinetic energy only. So, okay. Here this is a very important result will come. During the collision of gas molecules, they exchange their energy and finally average kinetic energy of the each molecule will remain same. That means one body has more energy, one molecule has more energy, one molecule has less energy. So, but the energies they transfer until their energy of the molecules are same. For example, half m1 v1 square is equal to half m2 v2 square. What does it mean? You mix oxygen molecules with hydrogen molecules. Oxygen molecules have more mass. Hydrogen molecules may have less mass. But even kinetic energies are going to be same. The m1 v1 square is equal to m2 v2 square. So, v1 by v2 is equal to root of m2 by m1 whole square. Velocities are depending on the masses. Kinetic energies are not depending on the masses. This is also a very important source for giving problems. The different gas mixes are given. What is the ratio of the kinetic energies of the gases they ask? So, therefore, 1:1:1 is the answer. It is the very best result, is a conclusion given according to the principles of kinetic theory of gases. So, what is the ratio between velocities of the two gas molecules at the same temperature? So, mass of the two gas molecules are given. What is the ratio of their velocities? Here we have to start the problem with half m1 v1 square is equal to half m2 v2 square at a given temperature. When temperature is constant, kinetic energy of the gas molecules is same. So, v1 by v2 is root of m2 by m1. So, this is one formula to solve the problems. Next, some of the laws we used in gases will reveal here. Charles' first law. V is directly proportional to absolute scale of temperature. V2 by V1 is equal to T2 by T1. T2 plus 273 by T1 plus 273. Generally, these appear in gases lesson also, but for those gases lesson, the main source is nothing but kinetic theory of gases. So, kinetic theory of gases developed these equations in the macro scope level, and this is assigned to the gases topic. And what is Charles' second law? This is called law of pressure or Gay-Lussac law also. P is directly proportional to T. So, P2 by P1 is equal to T2 by T1. Remember, here also you have to use Kelvin, T2 plus 273 by T1 plus 273. Next, Avogadro's law. So, what is Avogadro's law? At the same temperature and pressure, equal volumes of a gas contains equal number of molecules. So, this is called Avogadro's law. Okay, same temperature and pressure, equal volumes of a gas contains equal number of molecules. So, basing on that we can finalize. This is N1 is equal to N2. What is the Graham's law of diffusion? Generally, statement of Graham's law of diffusion is RMS velocity is inversely proportional to square root of the density of the gas. This happens at a given pressure and temperature. So, when two gases at the same pressure and temperature are allotted to diffuse, the diffusion rate is inversely proportional to the square root of its density. So, we derived the formula in this topic. Vrms is equal to root of 3p by rho. So, Vrms is directly proportional to 1 by root rho. Okay. And actually, all these laws are independently identified by the scientists. The Graham's law of diffusion is identified by Graham, Charles' first law, Gay-Lussac law, all these things were explained by the scientists individually. But how they are coming, they don't know in the initial stages. They know the outputs. So, later on, they started explaining the kinetic theory of gases. They came to know about the reasons of getting all these things. So, that is the reason why this lesson reveals the meaning of those laws. So, next one, to solve the problems in this topic, average velocity. Generally, what is the meaning of average velocity? So, some velocities V1, V2, V3, V4, etc. Vn is given. So, we can take them like V1 plus V2 plus V3, etc. by one number is given. 4 means 4, n means n, like that we will take. This is the average velocity. In this lesson, finding the velocity of an independent gas is difficult, no? So, that is the reason why, basing on the temperature, how to find out the velocity average. So, that is the specialty of this one. So, average velocity is given by root of 8 kt by pi m. Root of 8 kt by pi m. This is the average speed of the gas molecules. So, this is pi, this is m naught. M is for mass of the each molecule. This first formula used for molecules, where k is the Boltzmann's constant. Here you are using molecular weight. So, that is the reason you are using universal gas constant. So, this equation you have to remember. Next, basing on this, the random motion of the molecules are not responsible, random motion of the molecules are responsible for giving the temperature. So, if the systematic motion is existing, so due to that temperature won't be raised. So the random motion is responsible for the temperature of the gas. But actually what this means is, earlier in competitive examination, one question is given. So there is a jar, its temperature is equal to some 27 degrees centigrade or 300 Kelvin. So this is kept in a moving train. So train velocity is 60 kmph. So what is the velocity, what is the temperature of the gas? In this case, overall this jar you take, the center of mass of the velocity of center of mass is simply increasing. So net velocity is center of mass is changing. So due to this reason, the temperature is not going to change. So this is the meaning of the systematic motion is not responsible for the rise of temperature. The random motions of the molecules only responsible for temperature. Next, most probable velocity is one more term in this topic. Most probable velocity. So the most probable means the probability of existing a molecule or a velocity is more, then it is called most probable velocity. For example, some data is given how to estimate the most probable velocity. So these are all taken from statistics in mathematics. So 5 meters per second, 4 meters per second, 2.5, 4, 4, 5, 6, 4, like that it is given. So what is the possibility of the most probable velocity in this? The most probable velocity is given by 5 you take, 5 2 times repeated. Okay. 4, 1, 2, 3, 4 times it is repeated. So most probable velocity is given by 4 meters per second square. Like that they consider. Generally these type of most probable velocities in the daily life also they can use. Anyone want to stitch the dress, they don't take the average of all the people. So my dress, my size dimensions they have taken, your dress shirt dimensions they have taken. Like this 100 people's dimensions are taken. So to stitch for a common people, for ready-made dress, they take the average of all these dimensions, measurements. Generally it doesn't suit to anyone, no. So that is the reason why, which is the repeated size, they can consider that size of ready-made dress, they stitch it and they keep it in the shop. So that will be suited for many people. So like that. This is a way of finding the most probable velocity. Next, what is the most probable speed? How can you estimate the most probable speed? By using the temperature and all. Most probable speed we discussed earlier, which is repeated more number of times, is called most probable speed. But in case of gas molecules, many gas molecules are given. How can you find out the most probable speed? For that, a scientist, Maxwell, has given a distribution law. He has taken the gas molecules with a velocity range of, for example, some 10 meters per second to 20 meters per second, how many molecules are there. So like that he estimated. So number of molecules in a unit velocity range. It is simply, you can understand like this. In a classroom, students are all writing an examination. So paper is for 100 marks. So how to analyze your mark? So they can analyze it like this. So 0 to 20 marks, this number of students are there. 20 to 40, this number of students are there. 40 to 60, this much number is there. 60 to 80, 80 to 100, like that we divide. So, okay, 60 to 80 more number of students are there, means okay, paper is comfortable, so that more number of students got 60 to 80. So generally 80 to 100, naturally less number of students will be available. Okay, so in the same manner, 0 to 20 also less number of people are available. 0 to 20 less number, 80 to 100 less number, moderate range more number of students are available. So it is simply the meaning of distribution law. So number of students in a unit velocity range, like number of gas molecules in a unit velocity range, has drawn the graph. So this is dN by dV, dN by dV with respect to the velocity they are drawn. According to our earlier example, so in the less velocity range, less are there. This is in more velocity range, in this more highest velocity range also less number. In the moderate, lowest is also less number. In the moderate range, there would be more. For example, the temperature is at minus 150 degrees, this 150 degrees centigrade, average is going to be how much? At 20 degrees centigrade, how much is this? So like that we are estimating. This is for two different temperatures we are taking. It is not the major issue. So temperature T1, temperature is equal to T2, like that we are considering. So here you take, here the temperature T1 is going to be less than T2. Okay, dN by dV is going to be more in number. Highest velocities is going to be less. Here temperature is more. So that is the reason why velocity, peak velocity is more. Okay. So in this distribution, dN by dV is going to be maximum at this velocity. So let us suppose 300 meters per second velocity, maximum of dN by dV is existing. Like 40 to 60 marks range, more number of students are existing. In the same manner, here also dN by dV is maximum, more number, around 300 meters per second speed. Therefore, most probable speed is equal to 300 meters per second. Means dN by dV is maximum, then the corresponding velocity is called with the name of most probable velocity. So like that, if the graph is given, anyone asked the question, then we can answer it like this. Okay. Next part. He has given a distribution law. This is called Maxwell's distribution law. So it is a statistical equation. They look heavy only. So in this, to get the dN by dV value maximum and all you estimate, this part is going to be helpful for us to analyze. mv square by 2 kt value is equal to 1. mv square is equal to 2 kt. V most probable is equal to 2 kt by m, where m is the mass of the molecule, k is equal to Boltzmann's constant. You need to remember this one. This entire analysis is not required. This is the equation which you have to remember for solving the problems. But I am telling what is the background of this one. Okay. Next. What is the relation between RMS velocity, average velocity, most probable velocity? From this, 100% expected question is this. Vrms is greater than V average velocity greater than most probable velocity. Vrms formula you remember, root of 3RT by molecular weight, root of 2RT by molecular weight is average velocity, most probable velocity is 8 by pi RT. Just you take the ratio, once again, it will be appear like RT by M common, root 3 is to root 2 is to root 8 by pi. This is another important question. What is the ratio between Vrms is to V average is to most probable? Root 3 is to root 2 is to root of 8 by pi. So that you simplify. Vrms is to root 0.816 is to 0.92. So therefore 1 is to root 0.1 is to 0.82 is to 0.92. This is the ratio. This is area is important area for solving problems. Next, this was also questioned earlier. There are given temperatures T1, T2 and T3. A graph is mentioned here. PV by NT is the y-axis. X-axis they are given the pressure in terms of the atmosphere. Which is more? T1 is more, T2 is more or T3 is more? See, this is an ideal gas equation. So PV by NT is nothing but what? PV by NT, generally gas equation. PV is equal to nRT. PV by NT is equal to R. R is constant everywhere. R is constant means it is PV by NT is constant, which is called ideal gas equation. So therefore PV by NT is a gas equation, ideal gas equation. So these are actual gases. Which is more closure? T1 is more closure. So therefore, at high temperatures and low pressures, gases behave like ideal gases. See, this is having a more deviation from ideal gas. So that is the reason why temperature is going to be low. So from this, which is temperature is more means T1 is more, because ideal gases at high temperature and low pressure, they follow the ideal gas equation. So for that purpose, this is important. So these two expected questions.